Hello everyone and welcome to this webinar dedicated to the design of thin-walled and open cross-sections considering the effect of warping. My name is Tariq Shayban and I'm the product owner for Steel Coat Checks at Allplan. And in today's webinar, we'll have a look at how we can perform an in-depth analysis and accurate design of thin-walled or open section beams exposed to significant torsion. This will be made available through the new module called 7th degree of freedom, which is available starting in SCIA Engineer 26. So during the webinar, your microphone will be cut off, but do not hesitate to ask your questions in the dedicated segment, and I'll try to find some time at the end of the webinar to answer your questions. And as for the agenda, we will start with some theoretical background. So what is warping and why to use it. Then we'll see how to apply it in SCIA Engineer through this new module. And then we'll have a look at the new types of results that will be available now. And then we'll talk about some benchmarks which were carried out. And we'll have a look at also other types of analysis which are compatible with the 7th degree of freedom. And finally, we'll see how to use this new approach in code checks and specifically in second generation of Eurocode 3. So let's start with the theoretical background. What is warping and why is it important to consider it in structural design? So in structural design and finite element analysis in general, the 7th degree of freedom refers to warping of a beam's cross-section. So you can see it on the right side here. You can notice that the upper flange and the lower flange of the member do not displace in the same direction. So you see this distortion happening between those two flanges. So traditional 3D beam elements use 6 degrees of freedom per node. So 3 for translations in direction X, Y, and Z, and 3 for rotations. So warping occurs during torsion when points in the cross-section move out of plane, distorting its shape, like mentioned earlier, and what we can see in the figure on the right side. So the 7th degree of freedom captures this deformation directly in the model, enabling accurate simulation of lateral torsional buckling, torsional stability, and also second-order effects. So why and when is it important to consider warping in structural design? So first off, we can say that open thin-walled cross-sections like I-beams or channels are the most susceptible to warp, generating critical stresses alongside Saint-Venant torsion. As for other types like hollow tubes, they are less susceptible to warping, especially for beams with short spans where the Saint-Venant torsion dominates in that case. And warping must be included for lateral torsional buckling analysis when we have eccentric loads, connections with restraint, and of course second-order effects in steel frames, for example. And neglecting 7th degree of freedom overestimates deformability and masks instability, leading to unsafe design of bending plus torsion members. So we're going to illustrate this through a small example first. So we have modeled the following structure using two different approaches. The first approach on the left side, we have modeled it using 1D members, which have this channel cross-section. And on the right side, it was modeled using 2D shell elements to simulate this shape. So if warping is not considered for the 1D members, the beam model gives similar results to the shell model in terms of internal forces, and I will show you this directly in SCIA Engineer in a few seconds. And on the other hand, the deformations are much bigger in the beam model. As you can see, we have, for example, almost 3.5 meters displacement on the left side, which is really huge. As for the shell model, the biggest displacement is around 130 millimeters only. So without access to the 7th degree of freedom, a detailed 2D model is required with shell elements to simulate the real behavior of the members. What happens if we use 7th degree of freedom? So in this example here, we have kept the same model, but in that case, we have used the 7th degree of freedom option for the 1D members. And we can see that the displacement immediately went down to 130 millimeters, the 1D model, which is very close to the values for the 2D model. So basically now we have a solution with the 7th degree of freedom to have a valid approach for internal forces and for deflections. So it is important to note, and we'll focus on that later on, that it is also very dependent on the appropriate supports to get these results correctly. So we need to evaluate the transfer ratio of warping within a joint, and we'll see that in detail in the next segment. So now I will switch directly to SCIA Engineer to show you this small example. So we have the 1D models without 7-degree of freedom, with 7-degree of freedom, and the representation using shell models. So the loading is represented through nodal loads on the extremities in here. If we look at internal forces, let's say on My, we can notice that we have a maximum My of 1 Newton meter in here for the 1D models, and it's very close also for the 2D model. For the 2D model, of course, I used integration members to get the results as if it was a 1D member in here. So what happens if we look at the displacements? So if we look at 3D deformations, let's say for the example without 7-degree of freedom, you see 2,600 millimeters of deflection. And now if you look at the 1D model with 7-degree of freedom or the 2D shell, you see that the displacement is very close. We see an orange color, so somewhere around 120 to 140 millimeters. And basically, we can also have a look at 1D deformations. And if I look at UZ, you can see we have 130 in here, 128.9 in this 2D representation. As for the first model without 7-degree of freedom, you can see it 3.5 almost meters. So this is just to show you the importance of 7-degree of freedom without explaining in detail how to apply it. This will be explained in the next section. So what is the first requirement to use this module in SCIA Engineer? It's basically to have access to this new module called SCNS.07, which is available in the professional and ultimate editions of SCIA Engineer. The next condition is to activate the warping in the functionality tab, the project data. You can do that at any moment when you start the project or later on, of course. And it is also important to work in the 3D environment. So it works with frame XYZ or general XYZ. It will not work with a 2D environment, for example. And finally, it is recommended to consider shear center eccentricity in the solver settings to have the most accurate results possible. By default, in the new versions of SCIA Engineer, this option is unchecked, so we do not neglect shear center of eccentricity. And then we need also to make sure it is activated on the cross sections level. So basically, the 7-degree of freedom will not be automatically applied on all members. It will only be applied on 1D members for which the cross section has warping activated in its dialog. And we usually can use it for any type of cross section, but we have some exceptions. For example, if you use a full circular shape, you will get a warning message because basically the warping constant, IW, is equal to 0. So warping cannot be applied in that case. So we have this warning appearing once you try to close the dialog. As for the thin-walled shapes, it is not necessary to use the 2D FEM analysis because basically if we check it or uncheck it, the IW, the warping constant, is very similar. And if we use 2D FEM analysis, this will make the calculation a bit longer, so you can keep it as by default with this option unchecked. As for the thick-walled cross-section, in that case, IW will be equal to 0 by default. So it will be necessary to check the option use of 2D FM analysis if you want to consider warping in that case. And we'll also get an additional warning message if this cross-section is used with the steel or aluminum material, because for these types of materials, it is preferable to use a thin-walled cross-section. Then what about hinges? So basically, we will have an additional constraint which will be available in 1D members, on hinges on 1D members, which will be called warping. This could be set as being free, and this is analogical to having it as flexible with 0 stiffness. And in that case, there is no transition of the warping between the internal nodes of the hinge. So for example, if you look at this column connected to the beam, in beam A, if you have a hinge where we say that warping is free, it will not translate, it will not take the warping which would have developed in the column in that case. And of course, we have the option flexible, for which we'll have an additional parameter, which is the stiffness that we need to define in that case. And the last option is the option rigid. And in that case, there is a new condition, which is the transition condition of the warping deformation omega of two nodes of the corresponding hinge. And it is defined through a new parameter called transfer coefficient. By default, the value is equal to 1, but we can change it as we wish. And we'll see some examples later on that will let us understand a bit more what this transfer coefficient really means and how to use it. As for the nodal supports, we also have an additional constraint property associated to warping, which will be available. And in that case, we'll also have three options. The default option is free and is analogical to choosing flexible with zero stiffness. We also have the flexible option. We'll have also an additional stiffness that we'll need to introduce. And the last option is rigid, for which a full warping constraint is considered in the support. And you can see that the icon changes a bit depending on the type of constraint that we have chosen. And we now go to the next section, which are the new results available with this new module, the 7th degree of freedom. We'll start off with 1D deformation. So there is a new result for warping deformation called omega, which is present as a result on 1D members, and omega in reality is the derivative of the axial rotation px. So if you look at this small example, if we multiply the px that we have got, the omega, sorry, that we have got on the left side by the length of the member, we get the exact value of px calculated by SCIA Engineer of the rotation around the x-axis. Then we look at the 1D internal forces and nodal reactions. So first, in case warping is activated in the project, the torsional moment mx is split into two parts: primary torsional moment mxp and secondary torsional moment mxs. And we'll also have a new 1D internal force result, which is called warping by moment mw, which is in kilonewton square meters. And for the nodal supports, there is also a new reaction for warping by moment, mw, with the same unit, kilonewton per square meter by default. As for the stress results, in case warping is activated in the project, there is a change for stresses concerning 1D members on the level of normal stress sigma x. In that case, there is a new component which will be sigma x mw, which will be calculated based on the warping moment mw. And as usual for sigma x, we'll have the three other components related to normal force, moment around y-axis, and moment around the z-axis. As for shear stress from torsion, tau tor, if 7th degree of freedom is activated, this value will be calculated based on the moment mxp. If it is deactivated, it will be calculated directly from mx, in that case, the total torsional moment. And for total shear stress, it will be equal to tau coming from shear y plus tau coming from shear z plus tau coming from torsion, and tau, which is a new component, tau omega, which would be calculated based on if 7th degree of freedom is activated or not. If it is calculated based on mxx. If it is not activated, this new component, tau omega, will not be present in the model. And now we'll go and have a look at SCIA Engineer to see how we can set up the 7th degree of freedom module and how we can look at the new types of results. So in this example, as usual, you need to first focus on the functionality. So in the project settings, we'll need to go to functionality, and we make sure that warping 7th degree of freedom is activated. On the cross-section level, we have one cross-section, IPE 240, and you can see here that warping 7th degree of freedom is enabled. We can, of course, go ahead and edit it and deactivate it if we don't want to consider this phenomenon. So as for the boundary conditions, if you look at supports, you can see here that warping is set as being rigid, and you can see this new shape which represents the fact that we have blocked warping. And of course, we can also choose free or flexible if you want to. And the same thing goes for the hinges. So we have put here a hinge between the two beams. And in the first example, we have chosen warping as being rigid. And you notice that we have this transfer coefficient, which is added. And the first example will be used with a value of 0.5 placed on a hinge, which is on the right side. And next to it, we have the same configuration, but with a hinge placed on the left side with a transfer coefficient equal to 2. If we look at the new types of results, for example, if you look at 1D deformations, you see that we now have this omega available. And if we ask for omega, you can see that we have the exact same results in both modeling options. And you can see that the value on the left side is double the value on the right side. This is exactly due to the value of the transfer coefficient. So when we say it's 0.5, it means we take half of the value. On the other hand, if the transfer coefficient is equal to 2, we take double of the value from the opposite side. So basically, if you put it on the right side with 0.5 or on the left side with 2, you get the same result. And we also tested it with a negative value, so minus 0.5 or minus 2. And in that case, you can see that a value of minus 3.1 becomes a value of 1.5 on the other side. So it's divided by minus 2. What happens in the case we have a transfer coefficient of minus 1? As expected, we just get the same value, but which is inverted. And if transfer coefficient is equal to 1, there's a continuity in the displacement in that case. So it simulates a condition where no hinge is available, no hinge is placed in reality. So we would have gotten the same results as you can see in here where no warping hinge is present. And then we did also a small test where we have put very low and small values for the transfer coefficient, like 0.001 in here. If we put it on the right side, as expected, there is no transfer of warping. So in that case, the value of omega becomes 0 on the right side. So no warping is transmitted. On the other hand, if the hinge was put on the left side, the warping with the warping condition, which is rigid, and a transfer coefficient of 0.001, the warping is not available this time on the left side, and you can see the value of 0 milliradian per meter. And if you want to make it such as the warping being equal to 0 on both sides, what we can do is place a support, a nodal support instead of the hinge, and apply a rigid behavior in terms of warping for the support. And in that case, you see that omega is equal to 0 on both sides. It is not recommended to put the hinge on both sides. This is why for now I have always shown the hinge being placed on only one side because it can cause some issues in the solver. So either you put it on one of the two sides or you can also use supports as in here to simulate your boundary conditions. And finally, we'll have a comparison between a model where we have a flexible hinge where the stiffness is equal to 0 and a warping condition which is completely free. In both cases, you can see that the omega is not equal to 0, but if we put the hinge on the left or on the right side, we get the same behavior, same values of omega. So whether we use a stiffness equal to 0 for a flexible constraint, or we use a completely free constraint, we get the same behavior. And what is important to notice also will be on the level of the moments. So now, as mentioned before in the 1D forces, we'll have a new component, which is MW. So if you have a look at MW, when we have a flexible behavior with 0 stiffness or a free behavior, you see that MW is equal to 0, where we have the hinge. And the biggest value of MW is present where we have the torque moment, and of course at the support level. So basically we'll have very similar behaviors elsewhere, but it will depend on the boundary conditions. And we can also have a look at the primary torsional moment, MXP, and MXS also, where MX on the other side is equal to the addition of MXP and MXS. And if you look at the stresses, you can have a look at 1D stresses, for example. You have the new component, tau omega. So tau omega, as you can see, will have a switch from a negative value to a positive value exactly on the position where we have the torque. We can also have a look at sigma x, and sigma x obviously will now depend on the MW moment, and this is why we have peaks where we have the torque moment also. And the last option that we can have a look at is the reaction of the nodal supports, where we have now a new component, MW, and this value is, of course, equal to minus 0.6 in here, similar to the value of M omega in the beam itself. So now let's get back to the presentation and talk a bit about the benchmarks that have been done. First, there was a benchmark which was done to identify the transfer coefficients that should be used on an L-shaped column beam frame connection. So we have modeled this in two different ways, using 1D members or 2D members, and the structure is represented by an L-shaped frame with a moment which is a torque moment placed on the half height of the column. And here is the cross-section used for the example. And in both cases, we have considered three configurations for the connection between the beam and the column. So first is the diagonal. The second approach is to have a box plus diagonal, so stiffeners which are vertical, horizontal, and diagonal. And the third approach is having box only. And through the trial, we have noticed that the best way to represent the diagonal support, if you want to model it in the 1D model, is to use a hinge where we have put a rigid condition for warping, but with a transfer coefficient of 1. For box plus diagonal, it's the approach where we use a nodal support with rigid warping, where we have the best results. As for the box-only approach, we go back to having a hinge, which is having a rigid behavior for warping, but in that case, the transfer coefficient must be equal to -1. And now you can see the values of omega obtained in the 6 models. So for example, for box plus diagonal, which is the second example, for the 1D representation, we have a maximum value of omega of 107.6 milliradian per meter. And in the 2D representation, we have a very similar result of minus 105.8 in the column. And you can see that in the beam, warping is almost non-present in the 2D model, and in the 1D model, it's not present at all. So we have been able to simulate this behavior correctly with the very similar results in the 1D model. And what we also carried out is the modeling of the same L-frame and ANSYS using 1D members. And you can see here the variation of the results for phi x, omega, and the moment MW, and the two models in SCIA Engineer and the B model in ANSYS. And we can notice that the results for the 1D members are identical in the two softwares. So this validates that the approach in SCIA Engineer was correct. And of course, the results are both very close to the model using 2D shell members. And now we'll have a look at the second benchmark, which was used to validate the result of stresses. So we have used an existing example coming from the benchmark identified below, where we have a beam which is loaded with axial compression, biaxial bending, and torsion. The cross-section is IPE 200 and the steel grade is S235. So the numerical approach would, let's say, predict a value of von Mises, of the von Mises stress of 182.8 megapascal. So we have modeled this in SCIA Engineer 26, and we have activated the 7th degree of freedom. And we have also carried out in the past this benchmark in SCIA Engineer 18.1, and we were able to have a look at the results in the detailed Eurocode 3 check for the beam. As you can see on the right side, the bi moment, MW, is equal to minus 0.06. This is on the level of the midsection of the beam. And the maximum von Mises stress is equal to 182.8 megapascal. And now in the new version in SCIA Engineer 26, with the 7th degree of freedom, we can clearly see that the sigma E, the von Mises stress, is equal to 182.6 megapascal too, and it's also obtained on the same fiber called fiber 13 of the cross section. And if you look at the MW moment, we can see that the value is of 0.06 kilonewton square meter as predicted in the 1D model in the old version of SCIA Engineer, and of course in the benchmark itself. So now let's go to SCIA Engineer and show these two examples directly. So first, let's start off with the L frame. You can see the three different modeling and the equivalent loads which were placed in here to simulate a torque of 1 kilonewton meter. And we can have a look directly at the 1D deformations. So again, using the integration members, we can see the results on the 2D members as if they were 1D members. And we can clearly see that omega values are very close. And if I ask for the values on the local level, so you can see here where we have minus 77.3 in the column and minus 0.77.3 in the beam. It's because we have used a transfer coefficient equal to 1. And in that case, it goes from minus 77.3 to 77.3 because we have used a transfer coefficient of minus 1 in that case. And basically, we were able to predict which boundary condition to choose in the 1D member based on the results we had gotten in the 2D model. And then if we look at the benchmark, where we have the 1D beam, I have done the modeling also using two types of cross-section, which are identical, but for the first one, the 7th degree of freedom is enabled. For the second one, it's not enabled. So if you look, for example, at the 1D internal forces, if you have a look at MW, you can see that warping is available in the first beam where 7th degree of freedom is activated, but it's equal to 0 in the second beam where 7th degree of freedom is not activated for the corresponding cross section. And if we look at the stresses, if I have a look at the principal magnitudes, sigma E, the von Mises stress, we can see that we have 182.6 megapascal. And if I ask for it also in general for all fibers, we can see that on the second beam, the value is a bit smaller. I have 160.5 megapascal. So now let's go back to the presentation. And we'll have a look at other types of analysis which are compatible with the 7th degree of freedom. So basically, this new module is available with any type of analysis you carry out, whether it's a linear, nonlinear analysis, a stability analysis, or even a dynamic analysis. So we'll start with an example of how we can calculate the critical moment, MCR, based on the based on the linear stability analysis that we carry out on a beam for which the 7th degree of freedom is activated. So we have started with an example where we have a 5-meter beam with the following cross-section, and it is modeled both using a 1D member and also using shell elements. And if you have a look at the Eurocode 3 check in SCIA Engineer, if we assume that the load is destabilizing, i.e. placed on the top flange, SCIA Engineer calculates a value of MCR equal to almost 68 kilonewton meter. Now, if we run a linear stability analysis on the beam and on the 2D shells model, we can see that the first eigenmode, which corresponds to a lateral torsional buckling, has a very close alpha critical in both cases. For the Sells model, the alpha critical is equal to 22.86, and for the beam model, it's equal to 21.58. And in both models, we know that the my, the biggest value for flexural moment in direction y, is equal to 3.13 kilonewton meter. So if we multiply it by the corresponding alpha critical, we get a MCR, which is equal to 71.55 or 67.55 kilonewton meter, and it is very close to the theoretical value calculated in SCIA and the UCO 3 check. And then what we can also apply is a second order analysis which takes into account 7th degree of freedom. So the same example is used to demonstrate the impact of the 7th degree of freedom on the second order analysis. The following loading is applied. We have a compression of 100 kilonewton, My equal to 45 kilonewton meters, and an Mz equal to 7.5 kilonewton meter. And analytical calculations give a maximal displacement of 27.44 millimeters in the y direction and a value of 11 millimeters in the z direction. So if we run a linear analysis in SCIA Engineer, we have very similar results in both types of models. So we have a value of 27.7 or 27.6 millimeters in the y direction and values of 10.9 and 10 millimeters in the z direction. So what happens if we run a second order analysis? So if we look at the theoretical approach, the hand calculation would give a maximal displacement in direction y of 72 millimeters. So there's a huge jump on that level. As for the vertical displacement, it's still equal to 11 millimeters. So if you run the second order analysis in SCIA Engineer using a nonlinear combination, we get very close results to the theoretical ones. So for the 1D beam, we have a displacement of 70.5 millimeters, and for the 2D representation, we have a value of 69.1 millimeters. So let's go ahead and have a look at this directly in SCIA Engineer. So first, let's talk a bit about the stability. So as we mentioned earlier, we have considered its destabilizing. So we have put a load of 1 kilonewton per meter on the top flange of the beams. So this is a beam with 7 degree of freedom. In here, we have the beam without 7 degree of freedom. And the third modeling is done using 2D shells. And in that case, the load is applied as a surface load on the top flange, and we have divided the 1 kilonewton per meter by the width of the flange, and we get 6.67 kilonewton per square meter. So if you look at the 3D displacements, so let's start with the first eigenmode, which has an alpha critical equal to 21.58, and it appears on the beam which has a 7th degree of freedom. And you can see that it clearly shows a lateral torsional buckling of the top flange. If you look at the second value, which is an alpha critical of 86.64, it appears on the same beam with a different shape. And now on the beam without 7th degree of freedom, you see that the first alpha critical is 33.25, much bigger than the case where we have 7th degree of freedom. And we can notice also that the deflection has a different shape. It's not clearly a LTB of the top flange, it's more of a torsion of the beam. And if you have a look at the shells model, the first eigenmode has a value of alpha critical of 22.86, and you can see clearly that the shape represents a lateral torsional buckling of the top flange again, and it's very similar to what we have got with the 1D beam with 7 degree of freedom. So this establishes that we can now use this new warping approach on the 1D beam to calculate the M critical of a 1D beam in an easier way than having to model 2D shell elements. Now, as for the second order analysis, we have applied the loading that we have mentioned previously. We created, of course, a nonlinear combination, which has this load. And in the project settings, we have geometrical nonlinearity, which is checked. And of course, this would mean that in the solver settings, we can see the second order being available. So if you look at the results on 1D deformations for this nonlinear combination, you can see that we have a value of -70.5 for UI for the 1D beam with 7 degree of freedom and -61.1 for the shell representation. But in the case where we don't have the 7th degree of freedom considered, the value is only of -40. So it's really underestimated and can be very dangerous. So this is why the 7th degree of freedom can be really interesting to consider when we have a second order analysis being carried out. And finally, let's have a look at the usage of the new 7th degree of freedom module in code checks. So now in the second generation of your code 3, by moment is considered in a more direct way. So in the section checks, the warping is considered in the combined bending and warping check through the addition of formula 8.29 to account for reduction of bending capacity due to the by moment. So we can see the reduction of the resistance through the parameter BRD that you can see on the right side. And it is also considered in the combined bending and shear check, where the reduction of the bending capacity for shear now accounts for the bind moment. And you can see in formula 8.41 that the MYBRD is divided by MCYRD to take into account this reduction due to bind moment. And finally, in the stability checks, the warping is considered in the bending and axial compression check for uniform members in bending, axial compression, and torsion. So we can see both formulas C1, C2, where the by moment BED and the characteristic value of the by moment resistance BRK are taken into account. And now let's go ahead and show an example directly in SCIA Engineer. So we have created a project where we have a single beam on which we have applied two load cases. The first load case, we have a constant load of -1 kN meter applied on the full length and a torque moment of -1, which is situated at 1 meter from the start of the beam. And in the second load case, we have a point load of -150 kN, which is also at 1 meter from the start of the beam. So if you have a look at the ULS check, we have first chosen the load case LC1 on its own. And in the section checks, we have the option UC MY plus B, which is the combined bending and warping check. You see the value, which is of 5%, and we can ask for the preview. So in this detailed output, you can see that we have the combined bending and warping check available using formula 8.29. You see the design plastic by moment resistance, BRD, and BED, which is the by moment itself, is being used in the formula 8.29. And we can see the value of 0.05 in the check. And of course, the by moment BED is identified at the beginning of the report. You can see the value of -0.04 in here, where you have, of course, the table for all the internal forces. And if we go down a bit, you can see that we have also the stability check, where we had the combined bending and axial compression check, for which we have now the new formulas, C1 and C2. And as you can see, for these formulae, we have the value of BED and BRK, which are used, and we have a maximum value of 20%, which is calculated. And the new type of check, which is also available in the section check, is the combined bending and shear check. So it's used in UC M plus N plus V. If I refresh for load case LC1 on its own, the value is only of 0.23. So what happens in that case, if I ask for the report, we can see in here that this combined check is being done without considering the effect by moment, because it is clearly mentioned here. Since the shear force Vz satisfies criteria 8.35, its effect on the moment resistance about the axis YY is neglected. So in that case, formula C8 is used instead. But if I use the combination CO1, obviously in CO1 I have also load case SC2 which is present, so VZED becomes way bigger. And if we have a look at this check again, you can see in here that the new condition of VZED, which must be bigger than eta V multiplied by VPL is met. So in that case, the new formula 8.41 is used for this combined check, and you can see MYBRD being divided by C, MCYRD. And where do we get this value of eta V? It comes from the national annex settings. So we have a part dedicated to combined bending and shear, and you can see that the value of eta V is equal to 0.5 by default. And of course, we have the reference to the new Eurocode, and if needed, you can change this value in here. And so basically, this is what I wanted to show you in today's webinar. If you have more questions, do not hesitate to contact our customer service team directly on the email shown on the screen, and hope to see you again in the future. Thank you again for attending, and have a nice day, everyone. Bye-bye.